Hello dear students, here we start with the last topic of unit 2, that is sum of four squares. Before this we have studied that the numbers of the prime numbers of the form 4k plus 1 can be expressed as sum of two squares. That means the prime numbers which are of the form which are congruent to 1 modulo 4 can be expressed as sum of two squares. Then we have seen that prime numbers of the form 4 raised to m into 8k plus 7 cannot be expressed as sum of three squares. Then which numbers can be expressed as sum of three squares? That is actually open problem. That can be a research topic for you also. So you also can try a research on it. Okay. So now we come to the last part, that is sum of four squares. And here we are going to show that every prime p can be expressed as sum of four squares. But now when we express prime p as sum of four squares, it may happen that some of them may be equal to 0. That means, for example, 2. 2 is a prime number which we can express as 1 square plus 1 square plus 0 square plus 0 square. Then we say here 2 can be expressed as sum of 4 squares. So in this fashion, we are going to show every prime can be expressed as sum of 4 squares, but where some of the squares may be equal to 0. Okay, so now to prove it, we are going to prove the series of theorems. So here this is the first theorem. If p is an odd prime, then the congruence equation x square plus y square plus 1 congruent to 0 modulo p has a solution x0 y0 where x0 and y0 satisfy this condition. And now I have written over here or the next theorem. Actually, next theorem is a little bit different theorem, because here it states that if p is an odd prime, then there is an integer m with the condition that 1 is less than or equal to m less than p, such that mp is equal to sum of four squares. Okay, but still I have written it as or, because if the theorem 1a is asked, then first you have to write down the theorem 1, the proof of the theorem 1, and then you have to continue the proof of the theorem 1a. And therefore here both the theorems I have written as a one part only. So the proof we will first study of theorem 1, and then we start with the proof of theorem 1a. But that 1a will also include the proof of the theorem 1. म्हणजे तुम्हाला समजा theorem 1a हा परीक्षेत विचारला, तर तुम्हाला आधी theorem 1 चं प्रूफ लिहायचं आहे, आणि मग ह्याचं theorem 1a चं जे आता आपण प्रूफ बघणार आहोत ते कंटिन्युएशन मध्ये लिहायचं आहे. Okay, so because by proving this, that x square plus y square plus 1 congruent to 0 modulo p has a solution, we are obviously going to get that x0 square plus y0 square plus 1 is congruent to 0 modulo p. is congruent to 0 modulo p म्हणजेच काय आपल्याला मिळणार, it is of the form p into some number, that is we are going to get it is equal to m into p. ओके, मग हे इथे आपल्याला ऑलरेडी मिळतंय. मग त्याच्या कंटिन्युएशन मध्ये आपण पुढे काय प्रूव्ह करणार, की दॅट एम सॅटिस्फाईज द कंडिशन दॅट इट इज अ पॉझिटिव्ह व्हॅल्यू विच इज ग्रेटर दॅन और इक्वल टू 1 अँड लेस दॅन पी. दॅट इज व्हॉट वी हॅव टू शो इन द थेरम 1a. त्यामुळे थेरम 1a प्रूव्ह करताना तुम्हाला हे आधी प्रूव्ह करायचं आहे, आणि मग त्याच्यानंतर तुम्हाला एमची कंडिशन प्रूव्ह करायची आहे, दॅट इज एम इज ग्रेटर दॅन और इक्वल टू 1 अँड लेस दॅन पी. Therefore, I have written both the theorems over here, so that you can write down the proof of the theorem 1a by writing the proof of the theorem 1. Okay, so first part is to show that the prime p, for a prime p, we can find out the numbers x and y, where x0 and y0 such that 0 is less than or equal to x0 less than or equal to p minus 1 by 2, and similarly y0. So with the x0 y0 satisfying this condition, we are going to show that x square plus y square plus 1 congruent to 0 modulo p as a solution x0 and y0. Okay, so here we are considering the numbers between 0 and p minus 1 by 2. So here you have to remember two steps. First step is, since the numbers we are going to considering from 0 to p minus 1 by 2, first define the set S1. Okay, define the set S1 as 0 square, 1 square, 2 square up to p minus 1 by 2 the whole square. ओके, आता इथे असं लक्षात ठेवा, x0 आणि y0च्या व्हॅल्यूज बिटवीन 0 अँड p-1/2 मध्ये आहेत, म्हणून आपण हा सेट कन्सिडर करतोय फ्रॉम 0 टू p-1/2. बट नॉट ओनली 0 टू p-1/2, वी आर कन्सिडरिंग इट स्क्वेअर बिकॉज x0 अँड y0 सॅटिस्फाय विच इक्वेशन, x² + y² + 1. म्हणजे आपल्याला लागतात कुठले नंबर्स, x0 स्क्वेअर लागतो, y0 स्क्वेअर लागतो. देअरफॉर हिअर वी डिफाइन द सेट S as 0 square, 1 square, 2 square and so on up to p-1/2 square. Then first we will prove that no two elements of S1 are congruent to each other modulo p. कारण S1 मध्ये तुमचे एलिमेंट्स किती झाले, 0 स्क्वेअर, 1 स्क्वेअर, 2 स्क्वेअर अप टू p-1/2 द होल स्क्वेअर. म्हणजे नंबर ऑफ एलिमेंट्स वुड बी p + 1/2 झाले, पण ते सगळे स्क्वेअर आहेत. सो देअर इज अ पॉसिबिलिटी दॅट सम ऑफ देम मे बी कॉन्ग्रुएंट टू इच अदर मॉड्युलो पी, कारण ते सगळे p हून ग्रेटर आहेत. सो बट वी आर गोइंग टू शो दॅट नो टू ऑफ देम आर कॉन्ग्रुएंट टू इच अदर मॉड्युलो पी. सगळे p हून ग्रेटर नाहीत ऑब्वियसली. 0 स्क्वेअर, 1 स्क्वेअर कॅनॉट बी ग्रेटर दॅन p, बट सम ऑफ देम आर ग्रेटर दॅन p अँड दे मे बी कॉन्ग्रुएंट टू इच अदर मॉड्युलो p. बट वी हॅव टू शो दॅट नो टू एलिमेंट्स ऑफ S1 आर कॉन्ग्रुएंट टू इच अदर मॉड्युलो p. Okay, so here we start with the wrong assumption. Let if possible there exists x and y belonging to S1 such that x square is congruent to y square modulo p. इथे x आणि y म्हणायच्या ऐवजी आपण म्हणूया x square and y square. Let if possible there exists x square y square belonging to S1 such that x square is congruent to y square modulo p. Therefore p divides x square minus y square, then p divides the product x plus y, x minus y, but p is a prime number, so we know that if p divides the product of two numbers, if p divides a into b, then this implies either p divides a or p divides b. So using this Euclid's lemma, we say p divides x plus y or p divides x minus y. But what are the values of x and y? They are from the set S1, and S1 are the set of values from 0 square up to p-1/2 square, correct? And therefore x and y are the values which lie between 0 and p-1/2. So if you consider their addition, then from here you can easily see that their addition is less than p. So when their addition is less than p, obviously p does not divide x plus y. Okay, so here we got the result that p does not divide x plus y. So we are calling the result as 1, where we get p divides either x plus y or p divides x minus y. But in 2 we have got that p does not divide x plus y. Now on the next page we will show that p does not divide x minus y. See, it is obvious because x minus y is a value which is less than x plus y. Okay, so if you consider the positive value, that is mod of x minus y, then it is less than obviously x plus y, which is, and where x plus y is less than p. So again p does not divide x minus y, so we call it as 3. So from 2 and 3 we have got that p neither divides x plus y nor divides x minus y, and therefore in 1 what we get, that either p divides x plus y or x minus y. Here we get the contradiction to 1. Okay, and therefore our assumption is wrong, and therefore no two elements of S1 are congruent to each other modulo p. Now after defining S1, define the set S2 as -0 square -1 -1 square -1. म्हणजे तुम्ही S1 मध्ये डिफाईन केलेत एलिमेंट 0 स्क्वेअर, 1 स्क्वेअर अँड सो ऑन p-1/2 स्क्वेअर. इथे S2 मध्ये त्याला मायनस साईन लावा प्रत्येक स्क्वेअरला आणि त्याच्यातून -1 सबट्रॅक्ट करा. कारण हे आपण का करतोय, सी वी हॅव टू शो दॅट x0 and y0 are the solutions of the congruence x0 square plus y0 square plus 1 congruent to 0 modulo p. म्हणजे आपल्याला x0 स्क्वेअर मिळायला हवा -y0 स्क्वेअर -1. सो टू गेट दिस व्हॅल्यू, नाव वी आर डिफायनिंग द सेट S2 ॲज -0 स्क्वेअर -1 -1 स्क्वेअर -1 अँड सो ऑन. Okay, so here you have to define this, here you have to remember these two steps, how to define S1 and S2. So we have already shown in S1 that no two elements of S1 are congruent to each other modulo p, and S2 also contains contains the same types of elements, okay, with the -1. So obviously it is very clear that since no two elements of S1 are congruent to each other modulo P, no two elements of S2 are also congruent to each other modulo P. कारण ते जर समजा S2 चे कुठलेही पण एलिमेंट समजा तुम्ही congruent to each other modulo P धरले, so obviously that will imply the elements, two elements of S1 are also congruent to each other modulo P. Okay, and therefore we will get a contradiction. Therefore here we say directly you can write down no two elements of S2 are congruent to each other modulo P. Now clearly the number of elements in S1 is equal to P plus 1 by 2. I have explained you this. And similarly number of elements in S2 are also P plus 1 by 2. कारण इथे तुम्हाला 0, 1, 2, 3 up to P minus 1 by 2. 1 to P minus 1 by 2 हे P minus 1 by 2 झाले आणि प्लस 1 त्याच्यात ऍड केला की तुम्हाला नंबर ऑफ एलिमेंट्स मिळतात P plus 1 by 2. Therefore number of elements in S1 प्लस नंबर ऑफ एलिमेंट्स इन S2 इज इक्वल टू P प्लस 1. म्हणजे आपल्याला S1 आणि S2 टुगेदर मिळून किती एलिमेंट्सचे सेट झाले, किती एलिमेंट झाले, P प्लस 1 झाले. ओके, आणि आपल्याला माहिती आहे की नो टू एलिमेंट्स ऑफ S1 आर कॉन्ग्रुएंट टू इच अदर मॉड्युलो P, नो टू एलिमेंट्स ऑफ S2 आर कॉन्ग्रुएंट टू इच अदर मॉड्युलो P. देअरफॉर इथे जर P प्लस 1 एलिमेंट्स आहेत तर ऑब्वियसली वन एलिमेंट फ्रॉम S1 must be congruent to one element from the set S2 because complete residue system modulo P contains how many elements? Only P number of elements. म्हणजे फॉर एक्झाम्पल तुम्ही समजा P हा तुमचा 5 घेतला तर कंप्लीट रेसिड्यू सिस्टीम मॉड्युलो P कंटेन्स द एलिमेंट्स 1, 2, 3, 4, 5. ओके, आणि त्याच्यामध्ये जर तुम्ही 6 एलिमेंट हा ऍड केला तर ऑब्वियसली 6 इज कॉन्ग्रुएंट टू वन ऑफ द एलिमेंट of this set. That means 6 is congruent to 1 modulo 5. That means here if you consider the set of P plus 1 elements, कुठचाही घ्या, मग समजा आपण घेतला 8 तर you can see that 8 is congruent to 3 modulo 5. So in this fashion when you get the number of elements more than P, obviously two of the elements must be congruent to each other modulo P, and therefore from S1 one element is congruent to one of the elements from the set S2. So here we say let x0 now from S1 be congruent to minus y0 minus 1 from S2, and we get therefore this congruence equation, and therefore we get the required congruence equation, and therefore we can say x0 y0 is a solution of the congruence equation x square plus y square plus 1 congruent to 0 modulo P. Okay, where x0 and y0 are the numbers which lie between 1 and 0 and P minus 1 by 2. Okay, so here we have completed the proof of the theorem 1. Now for to write the proof of the theorem 1a, what we have to do, we have to consider this part. That means we have to consider that x0, we have to consider that x0 square plus y0 square plus 1 is congruent to 0 modulo P. आता हे आपल्याला कुठून मिळालं, हे आपल्याला थेरम 1 वरून मिळाले. ओके, त्यामुळे मी म्हणते तुम्हाला सारखं सांगते की इफ यू आर आस्क्ड टू राईट डाऊन द प्रूफ ऑफ द थेरम 1a, then first you will have to get this equation, and once you get this equation then you can write down the proof of the theorem 1a. Because what do we have to prove in the proof of the theorem 1a? That x0 square plus y0 square plus 1, there exists integers x0 square there exists integers x0 and y0 satisfying the equation x0 square plus y0 square plus 1 is equal to mp, where m satisfies the condition that 1 is less than or equal to m less than p. आपल्याला ही कंडिशन थेरम 1a मध्ये प्रूव्ह करायची. ओके, सो ही कंडिशन कुठल्या इक्वेशनसाठी प्रूव्ह करायची आहे, ह्या इक्वेशनसाठी. मग आपल्याला पहिल्यांदा दाखवायला हवं की हे इक्वेशन एक्झिस्ट होतं. मग हे इक्वेशन एक्झिस्ट होतं हे आपल्याला कुठे मिळतं, आपल्याला थेरम 1 मध्ये मिळतं. सो देअरफॉर आपल्याला लिहायचं आहे थेरम 1 आधी आणि मग थेरम 1a चं प्रूफ इकडनं स्टार्ट होतं. Okay, so we have already got this result from theorem 1 that x0 square plus y0 square plus 1 is equal to mp for m belonging to z. So now we have to show that m satisfies the condition that 1 is less than or equal to m less than p. हे आपण का म्हणू शकतो mp, because we have got the congruence equation from theorem 1 as x0 square plus y0 square plus 1 is congruent to 0 modulo p. Okay, so with that we can say that it is equal to MP, because this is divisible by P, therefore this is equal to MP. Now all of us know that square of a number is always a positive number, therefore this is a positive number, this is a positive number, this is a positive number. So when you consider the sum of the positive numbers and prime P is also a positive number, obviously M is greater than or equal to 1. सो ह्या कंडिशन मध्ये जे आपल्याला प्रूव्ह करायचंय 1 इज लेस दॅन ऑर इक्वल टू एम लेस दॅन पी, त्यातली एम ग्रेटर दॅन ऑर इक्वल टू 1 ही कंडिशन प्रूव्ह झाली. सो नाव वी हॅव टू प्रूव्ह दॅट कंडिशन दॅट एम इज लेस दॅन पी. Okay, so it is a simple part. For that, consider MP. So MP is equal to x0 square plus y0 square plus 1. Okay, so M is equal to, now this is a just simplification part. So I will not explain it in detail. Even if you read it, you will be able to understand this. Therefore we are getting M is equal to this. Then x0 and y0 are the values between 0 and p minus 1 by 2. So the maximum value for x0 and y0 is p minus 1 by 2. Therefore, putting that maximum value, we can say m is less than or equal to this value. Okay, so by simplifying this, we get this part. Then further, p minus 1 by 2 is less than p by 2, and therefore we are replacing over here the value of p minus 1 by 2 by p by 2. Then when you simplify this, you get this equation. Then again, p by 2 is obviously greater than 1. Okay, p by 2 is greater than 1, and therefore here we can say this part is less than p square by 2. Okay, and when you simplify this, you can see that you get this is equal to p. Okay, and therefore here we got the required condition that 1 is less than or equal to m less than p, and therefore here the theorem is proved. And therefore we can say there exists an integer m with the condition 1 less than or equal to m less than p, such that mp is equal to x square plus y square plus 1. But we have to show that mp can be expressed as sum of 4 squares. So we have proven the first part, that m satisfies the condition 1 less than or equal to m less than p. Now we have to show that mp is a sum of 4 squares. So if we have got mp as sum of 3 squares actually, so if either of x square or y square can be expressed as sum of 2 squares, then obviously mp can be expressed as sum of 4 squares. But suppose not, that is, suppose none of them can be expressed as sum of 4 squares, then we can write down mp as x square plus y square plus 1 square plus 0 square. So that's what I have explained you in the beginning of the theorem, that we are going to show over here that mp can be expressed as sum of 4 squares, but not necessarily each of them would be equal to non-zero. We consider that some of them may be equal to 0. Okay, now so we have got that mp can be expressed as sum of 4 squares, where some of them may be equal to 0. Now the next theorem is called as an Euler's theorem, in which we are going to show or we are going to get the result that if we consider the product of two numbers where each number can be expressed as sum of 4 squares, then that product also can be expressed as sum of 4 squares. Okay, so see, this proof we need not prove, because it can be just verified by simplifying the left hand side. So you have to simplify the left hand side first, find out this product, and then simplify the right hand side. You will get the left hand side is equal to right hand side. Therefore you can prove this result. See, up till now this result was never asked in exam, because it's very simple, very straightforward. Okay, but you have to remember these terms, because here we are getting that if each term is a sum of 4 squares, then that product can be expressed as sum of 4 squares. So this is the concept which we are going to use to prove that every integer n can be expressed as sum of फोर स्क्वेअर्स. कारण आता आपण काय प्रूव्ह केलं की एव्हरी प्राईम पी कॅन बी एक्सप्रेस ॲज सम ऑफ फोर स्क्वेअर्स. आणि आपलं एव्हरी इंटिजर एन काय असतं, इट इज नथिंग बट द प्रॉडक्ट ऑफ प्राईम नंबर्स ओनली. सो जर आपल्याला माहिती आहे की एव्हरी प्राईम नंबर कॅन बी एक्सप्रेस ॲज सम ऑफ फोर स्क्वेअर्स, आणि फ्रॉम ऑयलर्स थेरम इफ वी नो दॅट each if we get that product of two numbers where each number is the sum of four squares is again equal to sum of four squares, then by that we can express that every integer n can be expressed as sum of four squares. But students, here आपण आता p साठी नाही प्रूव्ह केलाय रिझल्ट. what we have proven that we have proven the result for mp, that every number of the form mp where m satisfies the condition that 1 is less than or equal to m less than p can be expressed as sum of फोर स्क्वेअर्स. मग आपण पुढच्या थेरम मध्ये प्रूव्ह करणार आहोत दिस m इज इक्वल टू 1 अँड दॅट विल इम्प्लाय दॅट एव्हरी प्राईम कॅन बी एक्सप्रेस ॲज सम ऑफ फोर स्क्वेअर्स. ओके, सो ऑफकोर्स तो पुढचा पार्ट आहे, तो त्यावेळी मी एक्सप्लेन करीन तुम्हाला. फॉर द टाइम बिंग व्हॉट यू हॅव टू रिमेंबर ओव्हर हिअर, just remember the concept that for any prime p we can express mp as sum of four squares, okay, where m satisfies the condition that 1 is less than or equal to m less than p. आणि हा Euler's lemma where we know that if every number is a sum of four squares, then the product of those number also can be expressed as sum of four squares. So using this theorem 1 and theorem 2, we will prove the next result about the numbers which can be expressed as sum of four squares. So that again I will give you the video in the next lecture, that is on Wednesday. Thank you.